I hope you do. Yes, thank you. Okay, guys, so hello again. We will have the, thanks for starting the recording. We will have again a lecture on data analysis, and today we will be moving into the last topic of our course. This is the deep learning, and for the deep learning we will have a 3 to 4 lectures left. So basically I will describe right now what you should expect from these lectures, and we will start from the simple things first, and then we will move into more advanced topics, etc. Just like the usual game. Okay, so basically the last topic, I hope you have enjoyed the previous ones. We had, starting from beginning, EDA, exploratory data analysis, without any sophisticated algorithms, no models, except a little bit with the PCA. Then we moved into the classification. Regression. Was first regression, then classification, then clustering. So basically, we've covered major methods that are being used in the usual data analysis or machine learning. And we just approached the deep learning, which actually will combine everything we've learned so far. And we will be utilizing lots of knowledge that we've gained during these months. That we looked into various methods. Because, for instance, when you apply the deep learning model on the classification task, during the evaluation, you just do the same as you would have done with the simple method. So we mostly will be concerned in looking at and will study the method itself, the algorithm and method, and how to fine-tune it, because there are some sophistications, because they're much more complicated, much more parameters involved and things like that. So this will be the major concern for the rest of this course. But what comes for evaluation, data preparation as well, what comes before the actual training and after, this is mostly covered. So basically, this is as simple as a task for me, because I do not need to cover these topics. I hope you know them already. But the drawback of this topic is that basically methods themselves are much more complex, even though they're based on the simple methods that you've learned so far already. Not so far, but already. So, okay, I hope this was okay for the simple introduction, and we can move on. I know that you had the last delivery yesterday. It was the deadline for the clustering, so I hope you enjoyed that. Clustering is not the topic we will be talking about during this topic. Okay, so basically we will start today the deep learning. And the deep learning, the difference with the usual learning. So for the usual learning, what we've been learning, we had in the beginning the input vector, and then we were looking for the method, right, for the algorithm, which would be on input vector. We would be learning weights, right? These were weights, and this was our algorithm or method. And basically, weights provided us a model along with the function, right? Function plus weights. We had a model, and with this model, the output of this guy, we basically were considered as a prediction. And this prediction, we basically tried to evaluate by using the error function of some kind, right? The error. And and oh, sorry, the error, basically we try to match with the actual value, right, the error. And then after that, we basically looked into the derivatives in most cases, right? So we were deriving error for some weight, right? For some J weight, for instance. And this was our gradient, so we can move and find out the optimal solution for the method. This was the usual learning, right? So then you go into the world of the deep learning, in the general sense, right? In the general sense. What we have now is we basically, again, we will be looking into the input vector. We have the same input vector. It might be much more complex. It might be the image, for instance. So image will have a matrix, a 2D or 3D matrix could be, even though we're not analyzing images in this course, but is a possibility. This can be. And we will talk about the kinds of neural networks that actually use them, that analyze images and provide some insights about the images, that can even generate images, right? So inputs can be much more complex than we've looked so far. Okay, so basically after that, what we will be looking at, we will be looking again at some kind of a function, right? Xi and W1. So let's put this as a vector of the weights at the first level. And this first level, we say that provides an activation, right? This is intermediate result for the input into another function, right? So we put here A1, W2. So there's another vector of weights that provides another intermediate results. So we can basically, what we can do, we can stack, you can think in a simplified way, we can stack multiple of these functions, right, in a line, in a sequence for the simplicity, right, until basically you will reach a JAFE, for instance, and this will be your weight JAFE plus 1, right? And this basically provides you the output vector. And as you can see, there is an output vector. So basically, in most of the cases that we looked so far, we were analyzing the single output value. So this time, we can basically provide not just a single value, we can provide a vector as an output, or even an image or matrix, right? So basically, the output can be much more complicated than before. But the key point, the key takeaway here is that we have a stack of multiple functions, and that could be function 1 and function 2. These guys can be very different ones, right? This is function JAFE, for instance. JAFE plus 1, whatever, right? This could be the separate different functions that will be learning on different aspects. So basically, what we have here, we have intermediate results. And these intermediate results are called activations. Activations, right? So these are activations. These are dates. These are values that go in the middle of some process, of some execution process, right? So since we have these intermediate values, this becomes a deep learning stuff, right? So again, at the end, we will be having some error. We can't avoid errors, so let's put the vector. Okay, this is a prediction vector, right? This is a prediction vector. This is the real output, so this is an error that we get. So in order to propagate back the error, right? So to basically to train these multiple weight vectors that we have right here, so we will have to propagate them back. So let's put something like, for instance, W1. We will have the partial derivative with respect to the vector on the layer 1, right? So basically something like this, I, and this is I, Y, I. Okay, and then we will have to calculate the partial derivative with respect to JAFE vector or whatever else vector. these derivatives are derived from the same error calculation function methods, different kind of functions here, right? We have a lot of weight vectors, so the propagation of errors is can be much more complicated in the deep learning. I see that I have bad network quality, so because of that, I will turn my camera off. Maybe this will. But if you experience any glitches in the network, please let me know. Okay, so basically what we get here, the difference I just want to stress here in an overly simplified way, that before that we had one function which is clear, and we learned weights that basically make this function provide output, the prediction, which is very close to the one we had in the training set. And here we will have multiple different functions that basically stacked together in lots of weights. So this implies that there are lots of quite a bit of more complexity with respect to the simple learning technique, as well as we have diversity of functions that can be stacked together. And this basically makes it a complicated task. As well, this already can hint you that in order for the deep learning to work, actually need much more data. One thing, right? We will be talking about this quite a bit, but you need more data, and you need a lot of quite a bit of complications in the problem. So the problem need to be more complicated than for the simple learning. Because you can imagine that having lots of weights for a simple problem, it will overfit instantly. So basically, it can learn just right away whatever you will throw onto it, because the number of weights is just tremendous, right? So basically, controlling the complexity of a deep learning algorithm is one of the key issues, key moments in the deep learning itself. Okay, so this is a short introduction that we had a simple learning method for one function, one set of weights. We have a multiple functions stacked together working on the same task, but having lots of weights, you can split these weights as a multiple weight vectors or a matrix of weights, but there are a lot more. And there are intermediate results. So basically, functions are learning on already something which was learned before, right? So this is not an intermediate input. This is something in between. So that's why the other thing which you need to understand, this complication makes it very, very hard to interpret the deep learning models. Simple models like that are hard to interpret as well. We've seen that, right? For instance, in regression, weights can be understood, but you have to consider the magnitude of values, etc. And sometimes then you engineer features, it becomes quite complicated as well to understand how it's actually, but it is possible, right? How it's influenced the final result, but it's all possible because the method itself is quite possible. Here, when you have an intermediate result, intermediate activations, you have lots of weights. This is almost impossible to understand how this beast works, right? So that's why these things are okay to solve complicated tasks like for instance, image masking, image classification, right? So pixel masking, etc. But to understand the internals, how it's actually being done, this is very, very hard. This is one of the drawbacks of the deep learning, that it's almost not explainable, right? Lots of researchers, lots of groups are working on that, and this is a big deal actually, to visualize these weights and to make use of them for the interpretation. Okay, so this is a short introduction to the deep learning, what it is. And now, more specifically, what we'll look at. So basically, for the remaining lectures, we will look into the deep learning aspects. So basically, deep learning is considered in the world as being equal to the neural nets, right? What I've described before is more or less the neural net architectural, right, with some simplification. But anyway, when you talk about the deep learning, and if you Google deep learning, you mostly will stumble upon the neural nets. So basically, this is the main topic for the remaining lectures. So we will be talking in the first lecture just today, right? We will be talking about feed-forward neural net, right? So this is the most simple flavor of neural networks that we will go through the full maths. So basically, I hope that after today's lecture, you will understand the maths behind the feed-forward neural net. So you will get some understanding how it actually works. Then the next lecture, obviously not today, we will not be able to cover that. I will be talking about various aspects of neural nets. So mainly we will talk about the training of neural nets, because there are lots of aspects in how to actually training can be done efficiently. About the architecture, how to construct, how to assemble a decent neural net so it would solve your problem. So I will tell you from my experience and the researchers about how it actually can be constructed so that it would solve your problem. This is still more an art than the engineering, but anyway, there are some practices that are used all over again. And so basically, like apartments. So basically, I hope that I will be able to deliver that. We will be talking about the activation functions. There are quite a few of them, so you need to understand which one need to be used where, what are the pluses and minuses for the activation functions. So basically, this is a crucial cornerstone, a crucial building block of a neural net. Okay, so then we will spend a while talking about the more complicated architectures of neural nets. So basically convolutional neural nets, recurrent neural nets, autoencoders, then self-organizing maps, and maybe something else, right? So basically, these are more towards the data analysis, right? More leaned not towards the artificial intelligence as in a broad sense, but towards the data analysis, so that you would like to learn something from data you provide, right? Okay, and then the last topic, I just basically included the last topic into the deep learning because this is a kind of deep learning, but this is not a neural net. So we will be talking about the ensembling. So basically ensembling, these are various methods, various architectures of the learning methods that combine machine learning models to get better results. So basically this will include various bagging, boosting, stacking, and so on techniques. And these techniques basically help to combine weak learners, some simple learners, into the solving some bigger task in a more efficient way. So basically, these 4 topics, which I envision for the reminder of this course, and basically in the frame of the deep learning. Okay, so what deep learning can? So let's turn into the neural net. So the main topic of today's lecture, right? This is a neural net. And let me start then the new whiteboard. Okay, so the neural net, if we talk about the neural net, right, it has a long history, right? So neural nets, right? So it has quite a longer history. So it basically starts in 1940s, something like 80 years ago. right? And I will put a few milestones which I consider not only myself but literature as well considers one of the cornerstone inventions, right, in the neural nets. So, for instance, in 1940s, there were lots of research on the human brain, on the biophysical neuron. And these researchers were led by the biophysicists, by the neuroscientists. And basically, they have envisioned, so for instance, if we talk about the first hype, right, I will put first hype, because neural nets have undergone something like 3 hypes over the history, right? So the first hype, it was, let's put it like this, roughly, right, was 1940s, 1960s. So this was the first hype of the neural net. So basically, lots of research in the 40s about the human brain constructions, about the biophysical neurons. And let's, for instance, say that work of researchers McCulloch and Pitts at 1943. Basically, they have suggested to reuse recent findings on the biophysical neuron and to put it into the logical operators that can be combined to solve complex problems. So basically, biophysical neuron, this is the usual thing that's being taught for the introduction of neural nets, right, is composed of like this. I will try to draw it, of course. Usually it's a picture shown, right? So this is a neuron, right? Neuron, human neuron. So this is a nucleus, right? Nucleus, right? And this is the neural cell, like this. I'm not a good drawer, as you know already, right? But I will try my best to make it fuzzy. Okay. And this is a axion, right? So these things, these are like branches, right, that reach for the connection with other neurons or other cells. These are called dendrites. Dendrites, right? And these are the ends that acquire electrical impulses, right? So basically, electrical impulse travels to the nucleus, to the neuron cell, right? And if it reaches a certain threshold, right, if the sum of all the electrical signals that travel into this neural cell actually reaches a certain threshold, it passes the signal, it creates a new signal and passes it over the axion, which actually ends up with multiple synapses, right? Synapse terminals, which actually connect to the other cells, right? Cells, if we want to provide a command of some kind, or etc., or to the dendrites of other neurons, right? So this might be the other neuron, right? This might be the other neuron. This is axion, etc. So this is a dendrite again, and this synapse actually provides a signal to the other neuron. So this basically research on the single element, on the simple element, which can be constructed in a chain, right? In a chain. This is another neuron, right, that provides info, etc. In this chain actually made an impulse for the number of researchers to talk about the possibility that this idea can be utilized for the computational problems. So for instance, these two guys, McCulloch and Pitts, in 1943, they've suggested to use the logical apparatus. So for instance, if you have a A neuron, right? The A neuron, and this is a C neuron, right? So basically, if this A neuron sends enough signal, so basically we have two branches, it sends enough signal, so this outputs as well. So basically this logical gate, this logical scheme is a equation of A equals C. So A basically sends a signal, and it's enough because there are two branches. We have two branches with enough of flow for the electrical signal, and C basically provides the same some kind of the output, right? So for instance, logical gate A and B equals C, right, would be a suggestion in this paper would be A and a single signal, right, through the single branch, and these two combined, right, basically triggers the C. These two combined triggers the C. Okay. The other type of gate, which we can envision, A and B, right? A and B equals C. This would be a gate of different flavor, right? So this would be two connections. This is sufficient enough to trigger the output, and this is enough impulse signal to trigger the output, right? So either both of these, either one of them is actually sending a signal impulse, right? C will trigger it out. So there are some flavors with knots as well, so suggested with knots, plus knots, other logical gates, etc. So all these were suggested back in 1940s, and this, as you can see, basically mimics exactly what the actually discoveries in the neurophysical neuron were made at the time. Okay, so now the next in the first hype milestone, right, was actually made by the Rosenblatt. We've talked about this as well. Rosenblatt. It was at 1957. This was the invention of the perceptron. And perceptron we looked at already. Some of you, I believe, have implemented it, right? So I basically will repeat it again. So this is your input vector, right? And this is a single neuron. This is a single neuron. So there are weights, right, on top of these connections, right? So basically there's a multiplication. And then there is a summation. And after the summation, we have a step function, right? So step function, if the threshold is actually above the value of 0, so by the original perceptron is 0, right? It's above 0, equal or above 0, we have 1 as an output, right? 1 or 0 output. So basically, this is the simple perceptron, right? And this simple perceptron was okay. It worked. It actually learned. It was able to backpropagate error. But problems, maybe I've already mentioned, like XOR problems, exclusive OR problems were not possible to solve this approach because this kind of problem is not divisible by the single line. So basically, this was considered a limitation of the perceptron. Okay, so this was a major milestone at the time, and throughout the next years, people actually have come up with the so-called multi-layer perceptrons that were able to learn XORs. So, for instance, the solution like this, xi1 and xi2. Right, so basically we might have three perceptrons stacked together. All right, so this would go here, here, and here, and these go here, here, and here. Right, so this is summation, this is a step function, this is summation, this is a step function. And this is again, we have bias 1, and we have the summation and the step function. So these all activations. Now 2 activations, this is 3 activations go in, this is 2 activations go in, and we have a yi, right? So this is basically a multi-layer perceptron. And this 3 perceptron system is basically enough to solve XOR. XOR, okay. So basically in the papers, researchers provide weights at the time, right? At the time provided weights that this is possible to solve it with multi-layer perceptron. But the problem was that this was not able to learn, right? So learning multiple layers of the perceptron was considered as an insolvable problem, because actually the problem was this step function, right? Which basically masks the error towards the latter layers. So this was actually the problem. So now we turned, it was forgotten this. Actually, at the time of this, until 1960s, for the first hype, people considered that we are about to have the artificial intelligence right away. It was considered that we are at the very rise of the artificial intelligence, and soon we will be speaking to machines. But it did not happen. And then it got into the Middle Ages, into the dark times, the artificial intelligence, not artificial intelligence by itself, but the neural network research, until the second hype. Let's do the second hype, and it was around 1980 and 1990, something like this, right, at the time. And actually, one of the cornerstones was Rumelhart, et al. At 1986. These researchers basically have made a huge progress, because what we did, they have suggested to replace the step function with sigmoid, right? So basically they have suggested this guy, and what this gave, actually, this gave a non-zero well-defined derivative everywhere. So a derivative now was able to propagate, because it was not just 0 and 1, it was some intermediate value which was able to divide for the latter in the chain actually forming, right? This invention basically made a breakthrough, and there were more inventions on this, right? Until, yeah, then 90s came, and a little bit later, basically new methods like SVM appeared, right? Like support vector machines, other methods appear, and they were considered to be better than the neural nets, because neural nets, you know, had their problems. The problems with neural nets mostly were vanishing or exploding. Theoretically, neural nets cannot be used in practice to solve the major problems. And it went again into the dark ages until the third hype, right, which started around 2010 and still continuing, right? You obviously know that we're in the hype of the artificial intelligence and deep learning. So we're here. So this actually was possible. The third hype started due to multiple reasons, but some of the reasons you can imagine were very, very small and tiny. Just an example for you, the work of Glorat and Benjo at 2010 What we actually did, they have looked precisely. They have made a research on the vanishing or exploding gradient problem, and they have discovered that actually the initialization of weights, remember, weights in the beginning we initialized by the random, right? Random initialization. So they have discovered that initialization of weights need to be done slightly different way. So basically the variance of the random generator need to be slightly tuned. And once they did that, the problem of vanishing and exploding gradients basically gone. As well, they have introduced a few more activation functions, and these functions worked better in the hidden layers. So basically, these tiny, very small tune-ups have changed the game. One thing, and the other thing, which I want to stress here and make a list actually for you, for your understanding of why actually everything kicked up for the neural nets and overall the deep learning. Okay, so reasons why it's such a big hype right now. Because we have lots of data. With lots of data, what we can do, we can solve the complex problems. You can imagine that for solving a complex problem, complex nonlinear problem, what we need lots of weights, right? We need lots of weights. So to learn lots of weights and to learn features from the small ones to the big ones, from micro features into the macro features, we need lots of data. So then complex problem and lots of data come together, we have the boost and the actual usage of the artificial neural nets, right? Because artificial nets suddenly started to outperform the usual data analysis techniques right away. Okay, the other thing was obvious computing power increase, right? So then the CPU, which was actually at the time was boosted by the Moore's law so far, right? But plus GPU, right? Coming from the gaming industry, right? Advances. Actually, this made possible to train networks in the decent time, right? In the time that you can still wait. So imagine before that, it was possible to construct a neural net, but to do a round trip, basically to get results and to start evaluating them, it might took, for instance, I don't know, a few weeks, right? So this was just not practical at all. Okay, so these two things, then we have already mentioned algorithm improvements, but I want to stress that these improvements were very tiny, right? Very small. So what we have right now, we have approximately coming technique from 1990s. This is not a new invention. This was already known and was used by the researchers in a small amount from already 30 years ago. All right. Then the other thing is when we started using these neural nets quite a bit in the research, it has proven that theoretical limitations, where were lots of papers about the theoretical limitations that I already mentioned, that they cannot be used and so on, so on. Theoretical limitations actually did not prove, right? They did not work out. So basically it was thought that, for instance, neural nets, due to their complexity and due to the amount of weights, will be stacking into the local optimums. But this did not happen, right? Usually this does not happen. This might happen, but usually not, due to various techniques and due to the nature of a neural net. In most cases, in the majority cases, it finds the solution which is very close to the global optimum. Okay, and the last thing, but not least, obviously, this is the great products and funding. Of course, with great products, we have a lot of funding pouring into this area. So basically, this boosts again more research, more people going in, more startups and companies starting using the neural nets. Okay, so we're so far in the third hype, and it doesn't seem to be going down. So basically, I hope this is from the simple researches, right? Simple research, simple things that kicked off by the natural neuron. And then it's gone through the long history of 80 years. There is research, there's tries and failures through the number of hypes. And now we are in hype number 3, which doesn't seem to be going down. Okay, so that said, I need to say a few more things about the neural nets for your major understanding. That neural nets can be used, can be constructed. This is a flexible thing, just like the human brain cortex, right? You can combine neurons into multiple ways. So this is basically up to the researchers how you combine it, right? So this is a very flexible thing. So basically, by combining, by knowing the task, what you want to achieve, neural nets can be used in multiple solutions, multiple tasks. So these are just, this is a list of tasks that neural net can be used for. So the first task is obvious. This is supervised learning. Then you have a output, right? And you want to make predictions. So this includes both regression and classification. And not like the other simpler methods, this classification does not need to combine multiple classifiers, for instance, like 1BS-all and things like that. This is just a combination of the simple classifiers. It can do multi-class classification right away in one method, right? So this basically binary, multi-class, and multi-label. So basically, neural net can be constructed in such a way that it solves the binary classification, multi-class classification. So basically, one out of many, of hundreds, right? And few out of many, right? Few out of many can be solved, right? With both predictions, with both hard or soft classification. Mostly it's soft classification, like a probability output, right? So regression can be a one output or vector, right? So it doesn't matter. It can provide a vector of various values, right? Or it can learn, for instance, a matrix, right? So, but this is a flexibility that you can design your neural network for. Basically, you specify the task. Okay, then we can use neural nets for unsupervised learning, right? Unsupervised learning. So this is mostly the dimensionality reduction. So basically, I will put the dimensionality reduction tasks. For the dimensionality reduction tasks, we have so-called autoencoders. So basically, you can shrink dimensions just like the PCA does into the smaller amount of dimensions. And in some cases, I would not say in most cases, because this is too powerful statement, but in some cases it works much better by practice, I can tell. So autoencoders, we will be looking into these, and I will explain you how these work. So these things, unsupervised learning, they do not require a teacher, they do not require the output beforehand. And then we will look into these self-organizing maps. Self-organizing map, SOM, right? So this basically generates a 2D structure so that you can basically arrange this in such a way that you can use it actually for the clustering as well. But in essence, it is the dimensionality reduction as well. So then we have a so-called area, the third one from the machine learning. This is reinforcement learning. Learning. So this is basically where we have a software agent takes action to maximize some reward and basically loops over, right? It makes an action, it gets a reward when it learns how to act accordingly. So it basically has some sense on the environment. For instance, it might have a sense on the screen output. Like a game, you can take a picture of the game, so the neural net will know the situation, right? It will try to learn an action, and after action, it will get a reward. For instance, Mario character has fallen over the cliff or has gained some coin, and it will be given back. So on a given input, on a given picture, reinforcement learning algorithm, neural network algorithm will know how to behave. And there are other areas where this is used. So, for instance, generative adversarial networks that generate, for instance, pictures, right? Fake pictures, fake images can be generated out of a noise, right? So basically like GANs, right? And things like that. So deep learning neural nets used in multiple areas, but we mainly, because we are in data analysis, right? We are in data analysis. We mainly will be looking into these and into these. Even though I think that for most of you, these are more interesting ones, but since this is data analysis and we're limited in time, we'll be looking into the major ones that are most appropriate for us. Okay, so these are basically tasks, and neural nets are quite liquid, so you can construct them on the way you want. Okay, this was how it took longer than I expected. Okay, let's get into the feed-forward neural net, and let's draw one, assemble one. I have here on a paper some simple neural net which I would like to draw, and we'll be doing the forward propagation and backwards propagation. So basically learning weights. Okay, so we start from the neurons, right? So basically, let me take some other picture which I think more appropriate. Okay. Okay, so we have 1, 2, 3 neurons in so-called input layer. Right, this is input layer, and we have 3 neurons. So obviously, input layer is defined by 1. This is a bias, right? This is a bias, just like we had in perceptron, right? And this is basically the input vector. So we don't have any freedom here. We have an input vector of parameters, right? Xi second. And this will be our input, right? So our input. So the first layer is predefined by the input vector. So there's no freedom for first layer. And we will call this from the first layer, we will call the 0 of activation, right? A0. So this 0 is the layer number. We need more parameters, more notations for the drawing, because this is deep learning, right? So we need numbering of layers. So this is numbering of layers, and this actually corresponds to the input, right? This is more or less corresponds to the input with except of a bias. So bias we will be calling activation on the 0th layer, and this is the 0th activation, right? The activation on the 0th layer on the first neuron. It was 0th neuron. This is first neuron, and this is neuron number 2 in the 0th layer. This is an input layer. Okay, so now let's draw the second layer. Okay, so 1, 2, 3 neurons in that layer, and this will be our hidden layer. Hidden layer. Okay, so this is hidden layer, and this will be an activation vector number 1. Activation vector number 1. And this is obviously A0 on first layer, A1 on the first layer, and A2 on first layer. Okay, so this is bias again. This is 1, right? So we do not take weights into that. So let's connect these all together, the other guys, right? Let's connect these together. And let's take these again to this guy. All right. Cool. So all these connections, right, between neurons, they are expressed as the weight vector for the first layer, right? This is a weight vector into the first layer. And how we will be calling the individual weights, right, later on. So I will be repeating this, I guess, once in a while. So basically weight is 0 and 1. This is the input, this is the output. So we know that this connection actually connects zeros, right? Zeros neuron in this layer and the first neuron in that layer. And this is for the first layer, right? This is input and output weight on the first layer. For the first layer, right? This is the target, what it's going for. Okay, and let's put the third layer, 1 and 2, right? This is A1 on the second and A2 on the second. And this is again our A activation number 2. Obviously, we will have connections here, just like that, and we need to connect everything, right? Fully connected. Everything is now fully connected network, right? We don't have any skips here. Okay, and again, so these connections have an associated weights for the second layer, right? So obviously this will be, for instance, this line. Okay, let's take this line, for instance, right? So this line, this connection between these two neurons are on the second, right? On the second, for the second layer. And this is 2, 2, right? The second neuron to the second neuron. These are the indexes. And let's make this is a final layer. So this is an output layer. Okay, this is an output layer. So basically these activations are the same like the predictions. So we can put, this is Y prediction, right? Y prediction. So we have a 0th activation. This is exactly the same like an input. Then we have 1 intermediate activation, right? 1 intermediate vector, and then we have the final activation, which corresponds to the output vector. Okay, but individually, this will be F1, Y, F2, and these are all hatted because these are outputs. Okay, so what we will be looking for, we will try to match these two to the output, which we get from the data set, right? So this is a learning task, right? This is a supervised learning task. We just want to get these, and these are coming from the Y vector, right? Output vector. Just for a little bit of complication, I have added 2 output neurons. So basically, this can be a regression task, for instance, for predicting 2 values. right? So for instance, this could be you input something like an earthquake data, and you want to predict the coordinates, longitude and latitude, right? You just want to predict, so you need two outputs. Okay, and now basically this gives us an error, right? This gives us an error, so we want to estimate this error. All right. So this is a toy neural net, which we just made for ourselves, and we will be walking through this neural net. It has an input layer, it has an output layer, and these two are predefined. We don't have any flexibilities, but we have flexibilities in the number of hidden layers and number of neurons in each hidden layer, right? And there are more options to choose, but so far let's consider these to be an option. Okay, so now we have only, even though we have 3 layers here, right? We call them input, hidden, and output layer, but we just have 2 vectors, 2 weight vector, right? Weight vector number 1 and weight vector number 2. So basically, that is why this guy is considered as 2-layer neural net. 2-layer neural net because it is only 2 vectors to be learned. The input layer is not considered as a true layer because it doesn't have an associated weight vector, right? So even though we see 3 layers here, it is considered a 2-layer neural net with 1 hidden layer, right? With 1 hidden. We can have multiple hidden layers, but it's something that just 1 input layer, output layer, and we can have multiple of hidden layers, right? There are more complicated architectures we will be covering later, but for now, just think of this like some limited possibilities. Okay, so what we have right now? Okay, so we basically have weights, right? And each weight vector is actually a matrix of 1, 2, 3, 4, 1, 2, 3, 4, 6, 7, no, 3 and 3, yeah, this is 6. We have 6 weights for each weight vector. We can consider this to be a matrix, right? A matrix. We can consider this to be a matrix, right? Okay, so basically we can express like this the weight on J's layer is equal to weight on J's layer. I will not be repeating that, okay? This is from 0 to 1, right? And from weight from 0 to 2, right? This is J's. Okay. And now we have the W from 1 to 1 and W and the weight from 2 to 1, right? And accordingly, W from 1 to 2 and W from 2 to 2, right? So basically, these are expressed as which neuron to which neuron, right? So this is an output neuron number, okay, and input number neuron. Okay, so this is a matrix of weights that we have in between, right? For this layer and for that layer. Okay, so basically in operations on the neural net or the training order, right? Training steps can be formulated like that. So first we have a forward propagation. So we have an input vector, right? And we predict the output vector, right? We have a prediction. This is a forward propagation, and this is the production. This is just the prediction, right? prediction. You can consider this as production, but technically this is a forward propagation. So we propagate values through the network forward, right? Then the second step is the total error calculation. You basically calculate the error, right? Okay, so you calculate the error. So error here can be so basically the sum, right? The sum of all the local errors, because errors can be considered as local ones because we have multiple guys output, right? We can tell that this is A1, E1 and E2, and this is a total. This is a local error, and this is the total error, right? So if, for instance, you are looking to train some weight on this branch only, right? So you just need to have the local error. But if you go to the branch like here into the upper layers, right? You need to estimate the whole error, right? The total error, because as you can see, connections go right here. Values are propagated over here. So basically the sum of local errors, right? So J, right? So this is a total error calculation. And now the third step is so-called back propagation. Back propagation algorithm. So we have an error, right? We have an error, and we basically from error back propagate into the weights, right? We just basically update weight matrices, weight vectors or matrices or individual weights, as you can call, backwards from the error. Okay, so having this said, let's take a look at the single neuron. Right, let's take a look at the single neuron, because the neural net is basically a combination, a network of rather simple components, and each component is just this neuron, right? So basically, by looking into the single neuron, we can draw a picture like this. So basically, this will be our single neuron, right? It has dendrites, like from the biological neuron, right? Inputs. And let's say that this neuron, this specific neuron, is activation on the ELF layer, right? ELF layer, and this is an F neuron, right? So this is number of neuron in layer, again, layer, and this is layer number, right? And let's take that this neuron is not the first one. So L not equal to 0, right? So this is not the first layer, because the first layer is a special layer, right? It doesn't have any weights and so on. Okay, so basically for this activation, we have a W, right? And this is L. This is associated to this layer weight matrix. Right, weight matrix, and the input is coming actually from the activation of L-1, right? Beforehand we had activations, right? Vector activations, and these activations are coming through and are being multiplied, right? The product with this matrix actually goes in. Right, and then we get in, we just basically sum it up, right? This is a summation process. Just like in the perceptron, we sum it up, and the summation, after summing it up, we get a value, so-called the net input, or we will be calling it Z on the ELF layer and F neuron, right? So net input of activation LF, right? This is the neuron specifically we're talking about, is this Zeph's value LF's, right? And it's equal to sum, basically, and it's equal to sum and we will be looping the jth iterator coming from the number of L minus 1. This is basically the number of L minus 1 activations that are coming in, right? And this is basically the weight JF, right? Whatever is here connected, right? These neurons, right? These neurons, right? So we basically loop them through J, and F is just me, right? Just me. And this is weight coming from L. This is coming from that guy, from that vector. And we basically multiply with the L minus 1, right? L minus 1. So these guys, L minus 1, these guys, and jth index, right? So basically, sum of products of these guys taking this guy. Basically, we multiply them, right? And we sum it up. And we have the net input into our neuron, right? This is net input. Or in matrix notation, we can put it in simplified way, right? This is L, right? This is weight matrix times the vector of L minus 1 activation. This is a simplified way, right? Writing it down. Okay, so once we have summed it up, multiplied and summed it up, we have a sum of these guys here. So now we can calculate the actual activation value, right? So our activation value is calculated by applying an activation function, right? So activation function J, we will be calling it J, the generic function so far, right? And we basically put in whatever we get into the net input, right? So this is an activation function. We just apply a function. And this will be equal to the value which will be provided by AF on L, right? So this is an output. Let's put it like this. These were the inputs, and this is an output. And the output is A, L, and F, right? This is a number, again, this is a number, this is a layer number, this is a number of neuron in the layer. Okay, so J is an activation function. And activation functions are the functions that provide non-linearity to the neural networks. And there is a flavor of them. There are quite a few of them, right? And we will be talking about this later on. But for now, you can consider them to be being as a, for instance, step function, the sigmoid that you know. Sigmoid or logistic function, right? A logistic function. You can consider this as a ReLU, rectified linear unit, leaky ReLU, and so on. We will be talking about these. I will explain you why and where these need to be used, right? But this will be later on because this is a separate topic on the architecture of neural net. For now, you just can consider that after multiplying all the previous activations with weights, we get Zeph's value. This is net input, and this net input we've put into the, let's say, sigmoid or just the linear function, right? And whatever we got out of this function, we just basically passed on, right, further in the network. Okay, so basically to put it down, after the activation function applied, so we basically have activation FL, the final output value equals to JZF on L flare. These guys can be different, right? Activation functions can be different with respect to layer, and can be even individual on the individual neurons. I haven't seen that in practice, but can be, right? You can construct them. But usually a layer has the same activation functions on its neurons. Okay, so I hope you understood that. the individual neuron. This is not difficult and not, I know that this is quite clumsy and quite complicated, but this is not difficult in essence, right? And this is not that different from the perceptron. This is just exactly the same. If you would have here an activation of zeros, right? You just sum up, you multiply by weights, and then you apply the step function. This is just the perceptron, exactly the same perceptron. So what you do, you take this perceptron, replace, for instance, with the sigmoid function, right? The step function with the sigmoid function, and stack these guys together in the structure like that. So you get your neural net. That's it. And this would be actually neural net of 90s. This would be a neural net of 90s, and it would have huge drawbacks, and it would most probably not train, but that's okay. This is for your imagination. Okay, so having said that, let's go and do the forward propagation. Okay, let's forward propagate. So the first task in training is the forward prop, right? Forward propagation. So this is, to repeat, this is exactly the same. Xi, we will be moving into the predictions. So you can imagine that the first forward propagation in the neural net is just on the randomly initialized weights. So the output is unknown, right? It's some random value. But with time, since we are doing many batches, many epochs, we will be learning something. But in the beginning, it's just a random output. Okay, so what are the steps? So in our toy network, right? So this is 4 toy artificial neural net, right? That we have defined up top, right? So you need to, we are just specifically doing this exercise for this toy network because this is much easier to understand when talking in the abstractions. By the abstraction, because there are lots of indexes, these indexes are not understood, this is hardly to understand, and so on. So we basically look into the toy. Okay, so the first step is basically we construct the first activation, the zeros activation, right? It's not the first, this is zeros. So what we do, we just basically combine bias with the input vector, right? So in our toy guy, the dimensions, right? The dimensions will be 2 plus 1 equals 3, right? We just added bias. Some networks do not have bias. You can choose, but usually bias is okay. Because remember, without bias, we need everything centered, right? Bias basically gives you a possibility to learn shifts. Okay. So basically, this is how we calculate the input, right? We first the zeros activation. Then what we do, we basically calculate the first net input into the first layer, right? So we basically do the W of the first and times activation of the zeros, right? We can transpose or not. It really depends on how you lay down your vectors, etc. But I just basically repeated what we had right here, right? We just calculated the activations, the inputs, right? The input, the net input into the first layer, not activations, the net input, okay? So after doing so, what we will have, so the dimension will be, we had a matrix of 3 times 2, and 3 times 2, and the activations on zeros were 3, right? So dot product with 3, it is 2, right? So Z input it is equals to 2 because 3 goes away because we have a dot product. We have matrix multiplication. So basically, by looking into this network, we have 2 net inputs, right? 1 net input and the second one. We had 3 guys times these 3, right? And this basically gave us two inputs, because this is vector of the four matrix of the weights. Okay, so we have dimension of 2 right here. Now we calculate the activation number 1 in the hidden layer, right? So this is, we add again, we add bias, right? We add bias, and we basically apply the activation function on top of what we have calculated as a net input. Okay, so this is again dimension 2, which we had from the net inputs plus 1, and this equals to 3. Output from the activation from the hidden layer is actually 3, 1, and whatever we have calculated over there. Okay, so again, the net input into the output layer, into the second layer, right, is equal again weight on the output layer times activations on the first layer, right? Whatever we have taken from the first layer, we just basically multiply and sum with the weight matrix, right? So again, this is again the same picture. 3 times 2 dot product with 3 equals 2, right? And again, output is 2. So here, and on the final output layer, we have activation second is equal to activation function applied on the vector of the net inputs. And here, since net inputs are 2, right, we have a dimension of just 2 outputs. Yep. And this is what we have. So we basically have gotten our predictions, right? So these are our predictions. And our predictions are a 2, right? So basically our activations, outputs on the output layer is basically the predictions. All right. So we basically went through beginning to the end, right? Beginning to the end. We just one pass, one vector, one pass, right? One input vector, one pass, one output. Okay. So what we basically learned, but we have applied, and we will be learning one weight matrix and another weight matrix, which is something like 2 times 3 times 2, something like that. All right. Okay. Good. So now let's calculate the step number 2, and this step number 2 is basically the error calculation, right? So for the error calculation, this is error calculation. So for this specific task, we will make it just a simple local error. We will calculate as being error of I. This is the of J. Let's put J, right? This is output neuron number, right? Number of output neurons. So this is a local error will be. Let's make it half, because we want to get rid of the in the derivative of some values, right? To make a simplification, and this will get Yij minus Yij hat with prediction. The actual value minus the prediction and squared. Right, and this is a reminder to you that this is whatever we got from the output layer, the final layer, right? Okay, and let me take it like 2. Yeah, 2. Okay, so this is the local error, and the final error, the total error is basically the sum, right? Sum. And J equals 1 until 2, we have a J, which is basically sum these errors, so we get the global or total error. Okay. That's right. So basically, we just approached to the backwards propagation, to the back prop. Back propagation, and this is quite a lot of things. I think if I would move into that topic, we would stay here for another hour. I think we can make it the next lecture, if you don't mind, because this is quite an extensive thing. We need to back propagate this error we just have gotten into the weights. So we need to estimate how much of this error, how much of this difference was actually reflected in one of the weights. And we need to fine tune these individual weights in our toy network. So I suggest that next week we will cover the topic of the backpropagation. So basically we will look into this algorithm, and then talk about the architectures, about various architectures, about how to construct the networks, etc. Okay, so basically we have enough lectures before in front of us, so I think this is no rush. So I want to finish here, unless you have some questions. Please go ahead. You can tell otherwise. So your homework, I believe, okay, I think that I have a question, right? Because everything boils down to the homework. So for the homework, if you want to start it right now, so I think that I will give you a precise plan how to proceed with the homework, but it will be more or less such that you will have to choose a task, since neural nets are so flexible that you can invent a task for yourself, right? But the simplest to take something that you had already as a task. So for instance, a classification, a regression, or whatever else, and you have gotten some metrics, you have evaluated that. So you can take exactly the same task. Please pick something which is more complicated, which is a complicated, not a simple one, right? And try to attack it with a neural net. And it will be an interesting thing, because your goal will be to construct a decent, well-working neural net, not to code it yourself, but to construct by using the Keras or TensorFlow library or PyTorch. It's up to you. You can construct it, right? You can play around. You can look up the best architecture that doesn't overfit. And then it will be interesting that after evaluation, you will see the difference. You will be able to compare the results that you've got with the some machine learning, maybe your implemented algorithm, and the one that's with the neural net. Okay, so the plan, the more precise plan and steps, I will give you later on. But for now, that's it for today. If you don't have any questions, so have a nice evening then, and talk to you next week.